All right, welcome everyone. I know it's late. Thank you for staying. And is it a little bit much? Can we do that? Okay. So yeah, thanks for holding out. We're almost done. One more session, and we'll have that sweet, sweet weekend. So welcome to Rediscovering Fire. The title really alludes to the fact that this is not really anything new. This is more of a curation of the lessons, of the things that I've learned in the process of the past couple of years. But I think the field overall has known this for a very long time. So I'm, as you can say here, see here, I'm Jørgen. I work for Equinor as a developer. Over the past few years, we've developed quite a few libraries to work in particular with old oil and gas industry file formats. They're very often very old, they're very crufty, and they have a lot of problems. They're not easy to work with, and we're trying to sort of alleviate that pain a little bit. Largely, these examples are taken from segyio, but we've applied the same architecture with quite good success to a couple of others. DLIS.io is one for well logging. Segway, which I'm going to talk about, is about seismic. But they all have the same fundamental architecture. What I think is rewarding about this, they're all open source, so it's very convenient to talk about them because you can actually see these lessons for yourself, so to speak. And it's given me a greater appreciation of why a lot of the libraries that I have interacted with over the years, it's given me a greater appreciation of why they've done what they have. You know, you kind of realize, oh yeah, so that's why they're doing it and what the benefit of that is. So let's, this is the outline. We're talking a little bit about the why. We're going to briefly cover API and ABIs. The design for primitive types on the no allocation policy, on call and core functions, and also how to design primitive functions. So all these examples are from segyio. It's, as I mentioned, it's free software. It's the LGPL 3 license. It's distributed now in Debian and Ubuntu of the big distributions, but also mainly on PiPI, where most of our users come from. It runs on a C99 core, which I deeply regret was not written in C++ with the C89 interface. It's written in C99, and for the next time, we've sort of fixed that by writing it in C++. And currently has fronts in C++, 11, Python 2 and 3, and we have some experimental stuff in both C++ and Julia. It is in the sort of open geoscience community, which is getting pretty large now, actually. This is the de facto library for reading and writing seismic data. And if you ever want to check it out, it will be available here on GitHub. So let's start with, oh yeah, by the way, I checked it out this morning out of curiosity. I went to PiPIstats.org on the internet and just looked us up. And it turns out we have about 12,000 downloads last month, which is pretty staggering. Now, I think a lot of that are bots, but it's telling you a little bit about its usage. In terms of, you know, how niche this really is, this is pretty huge, and we're very proud of that. So let's start with some whys. So we have a pretty clear goal. The goal is to have a single and fast portable core. And I mean portable in the true sort of old Unixy sense. We run on multiple operating systems and multiple CPUs, including S390, which is an old IBM architecture, which I have actually never used myself. But Debian helped us test and run with that. We want to be able to support multiple integrated language fronts. And by that I mean we don't just want simple language bindings. They're pretty awkward. It feels like you're calling into some third-party solution by essentially forking out and running a process and then just, you know, parsing the result. But we wanted something that you can actually feel integrated with, that would behave as if the whole application was written in the same language, right? We wanted a clean upgrade path so that you basically, if there was an upgrade to the core because there was a bug or some internal, you know, fix, you could simply replace the shared object and everything should just work. And in fact, we have done just that. by adding support for more numerical data formats. And sort of the summary of that is that we wanted to build a library to build libraries, right? So the goal is not to build a library for the application developer to use, but for the library developer to use. That distinction is remarkably important, or rather has pretty big consequences when you start diving into the details, because the assumption that goes into that are quite different. In short, I think it is important that the user-facing library feels right. Okay? So what I mean by that is that we want more than to just invoke some external process from, in our case, largely Python, but this applies obviously to every language. What we want is we want to be able to manipulate the input and states and parameters from Python as if it was just a native structure and have that be very effectful. So for instance, in the case of different numerical formats, you should be able to say, you know what, this has this numerical format, and please interpret the bytes differently, right? So simply copying structures for post-processing it's not enough. So a good example, I think, of that, if you're familiar with Python, is NumPy. NumPy never really feels like anything but Python, but most of NumPy is written in C and Fortran, right? And you never really feel like it feels Pythonic. You know, you can deal with the structures internally that way. We also want to be able to maintain a lot of the code to have sort of a single source of truth and authority without actually having to change clients. And that means having a core that would be shared when you have multiple language fronts. So improvements that happens now that we detect through Python will immediately benefit our users that come from C++, right? And we want to be both forwards and backwards compatible as much as possible. And then there's also a matter of style, you know. Python has a very opinionated style on what programs should look like, and you should facilitate that, but that is not at all compatible with how Haskell programs look, right? And you want to be able to accommodate both. And in order to do that, you need to be very careful when you're designing something that is supposed to serve both. You can't just design a Python library with C syntax and hope that it will work, because it doesn't. So let's dive right into some details and some definitions. Because in a lot of languages, a lot what has happened here when you talk about your JavaScript and your C#, right? There's really not that much of a concept of an ABI, right? There's never any talk of the binary interfaces of things. Because everything is either exchanged as source or as this unified runtime binary dialect thing that runs on the CLR and then the JVM, right? But when you're dealing with native code like C++ and Fortran and Rust, you have your calling conventions, right? You have everything. When you change signatures like that, it's not something that is annotated with it. And then if you're invoking the same symbol with two different definitions, then it's going to crash, hopefully. A lot of the time you just get very, very corrupted results, which is actually worse, I think. And maintaining ABI in particular is not very straightforward. It limits the set of changes you can do. Usually, though, you do that for a good reason. And I think a stellar example of that is Qt. They have done that for years and years, and they are very, very aware of it. So let's have a quick run through of the definitions and what that means. So API is probably the more familiar because that applies everywhere. You know, it's your application programming interface. And a brief summary of that would really just be what you see here, right? It's your function signatures and your types. And it's a property of, it's about source compatibility, right? And it's a compile time property if you're going through the compile step, as you do with a lot of languages. In short, the effect is that programs that worked with the old version should, with recompilation, work with the new version, right? And there are a lot of API compatible changes you're able to make. An example would be to change your integer to a long, and promotion would happen and you wouldn't care. Or you can add members to a class and no one would know the difference, right? You can, as long as you add them at least at the end, because sometimes they're order sensitive. Both of those cases would violate ABI compatibility. So the ABI is the application binary interface, and it governs largely data type, size, and alignment. Alignment is fortunately something that most people never ever have to think about, but when you do, it's quite painful. And this is a runtime property. And really, what we're trying to accomplish is that programs that were compiled against an old version should, without modification or recompilation, work against the new version of a library. And of course, maintaining ABI compatibility will give you a very clean upgrade path. Compatibility has the caveat that it's sort of implied that you're running on the same toolchain. Binaries are very rarely compatible across compilers. Of course, maintaining your both ABI and API compatibility makes your clients very happy because it makes the upgrade path easier and their code never just randomly breaks because now they can just drop in a DLL or an SO and you're happy. And, well, I mean, you don't break their code, right? In order to maintain this, there are a few rules you can follow. And if you do this, you will almost never, ever have problems. So if you never remove functions, if you never change arguments, that means no adding, no removing, and no type changes. You never change your structs, you should be fine. Because you can add whatever you want that doesn't remove or change anything. With this, you should remain stable. But how does that work over time, right? Well, it helps if you design for it. So let's talk about how we accomplish that, right? So it starts with this emphasis. So just so we have it clear, your primitive types, they're your ints, your floats, your pointers. Structs are not. They're sometimes also referred to as aggregate types. And they're nice in C for API purposes. And just keeping things together is much more convenient, passing one value around than 10. But it does put a lot of requirements on the callers. The primitive types are much easier. Sizes are known. They're very universal. And if we were just in the C world always, or C++, then this wouldn't be so much of a problem because obviously you can read it because they're native. But the structs tend to break down the second you cross your your language boundaries. Every FFI, your foreign function interface, I'm going to probably abbreviate to FFI from now on, but that means foreign function interface. That is your procedure of calling a piece of code written in a different language from your language. C I'm talking about because it's very universal. Every language has a FFI to C, but very rarely other languages than C, largely because C is so ubiquitous and simple. Well, they tend to work very well with primitive types, but they have a lot of problems with structs usually. With primitives, runtimes like Python tend to be able to convert your primitives automatically, but that does not apply to structs. Then you kind of have to replicate the fields in the right order with the right alignment and hoping you get that right with no static checking and also a lot of other sort of restrictions in your host language. So in order to illustrate that, I've created a little example. So this is a modified or simplified address info struct from C, if you're familiar with the C standard library. And the same struct if you would have to be compatible with that in Python. Now in Python, this works it works like this in most languages I know. I think C# looks almost exactly like this. You register your variable names, their sizes and alignments in a class or a class-like thing. In Python, you use the special fields member you get when you derive from the C-type structure. And this is the output of the getAdderInfo function in C. As you can see, if you're familiar with Python, this looks pretty awkward, right? This does not look nice. It very much looks alien. And of course, you're interacting with something that's foreign, so that's not so weird. Usually, you would stick this in a library, and you would never really know. But still, it does. So it's not very ergonomic, right? to call the address info function from the C standard library, you would pretty much have to do something like this in Python, right? You would use the byref function from ctypes to obtain a pointer to your address info struct. You would pass that, and then you would maybe inspect a result. If it fails, you would have to inspect the error code. I'm not doing that now for simplicity, for brevity. But there's of course no automatic exception happening here. You would have to do that manually. And in effect, what you would do is you would write a C with Python syntax mini language around your language boundary. That being said, this is not so bad. Okay, it does force us to make the compatible struct, which is you need to maintain the mirrored structure exactly as if it was designed in a header. It's easy to get wrong, and it's very obnoxious to debug. But that's usually done once, so that's not the end of the world. But now you still need to make the struct for that function call only. You can't reuse it for anything else, and you can't really interact with it directly. It definitely does not feel like Python. In Python, you would want something like this returned. The members are C types, though. If I just go back a little bit, you can see that the members are the C types cint. But we don't want that. We want native Python. You know, we want it to feel like a Python library, like it's integrated. Because this is the problem with the C int. It's not actually an integer. It's a memory allocation and a hint that it's an integer. So you can get it with .value, and most FFIs have some detail like that. Sometimes conversion is automatic, sometimes it's not, but you sort of need to pull it out from there. But you can't sum it with an integer. You can actually keep it around. You need to convert it at some point. So we don't want to keep the FFI details around for very long. If we instead just use primitive types to communicate this, our call itself is a little bit worse. And this is even worse because, of course, we need to get 3 values out. But notice that we have no sort of forced representation or need to keep these around in a struct or in a class anymore. So we don't have to make this compatible struct to make our function work. But if you wanted to group them together in a not necessarily even compatible struct, that's easy to do. You just put it in a class and have these as members, and you will be no worse off than you were before, but at least now you have the flexibility. And in fact, when you have multiple values like this is essentially a struct anyway. It's just deconstructed a little bit. So it's less restricted, but it has all the same properties. And it's no worse in terms of signatures and binary stability, right? If you would do anything for an ABI break here, it would also be an ABI break if you use the struct. It's no worse off. Although usually when you pass integers or primitive types by value, you can usually go from a Python int to a C int in C types in Python automatically without any issue. What's nice too is now Python always owns the variable, and there are no lifetime issues with that. Let's look at another example, because this is what I have usually seen and which sort of motivated me in the first place to do this design. So we have this function getData, which gets some data from something we don't know exactly, and it returns a pointer to our blob. Our blob is our class with something. It's our object. We don't exactly know what's in there, but we know that we can point to it. This reads from a huge memory pool, and it gives you really something of a size at some offset. Now in Python, we use this getData function, and we get a pointer to this blob back. And we've sort of cheated a little bit, and let's assume now that you don't even have to unpack the C pointer, and it just immediately gives you back a Python object-ish. But you add this to your two of your graphs, who are now responsible for releasing that memory. Who owns this memory? This is now not clear anymore, because in Python you have no such distinction, right? There's no such annotation either. You cannot distinguish the owners from each other, because in Python that concept just doesn't apply. And also, really, you cannot distinguish different kinds of failures this way, because all the information you're getting back from your getData function is if blob is a null pointer or not. So you know that it failed, but you don't know why. So it's impossible for Python now to actually report to the user what went wrong, which is a pretty glaring design flaw. What you can do technically is to hook and register blob as a type and build a hook into your garbage collector. But that's very indeterministic because you don't know exactly when your garbage collector is going to run. With all this focus, we're going to come a little bit back to aggregate design later, but with all this focus on primitive types, the most useful of those, I think, would be ints, right? And this is something that I noticed happens a lot in the C standard library. They use ints for virtually everything. And it kind of struck me as clumsy, especially if you started programming after the 1990s, where you had a lot more sort of structured data types around. But C stuck around, and the question is, why are integers so great? Well, they are, so use them for everything. The integer, the number, is sort of the fundamental data type, both for your CPU and in your language. And they're quite powerful when you pair them with conventions and semantics, right? So for instance, in segyio, virtually all functions return an integer, and that's the status code. What was the outcome of this operation? Did it work? Did it not? In case it failed, what exactly did fail? Can you at least shed some light? Can you at least point me in the right direction? And then convention and documentation tells you what are the state of your output variables from that. Ints can easily be received and passed along and managed without any particular structure. And in fact, most runtimes too optimize heavily for integers with a lot of cool techniques. They're very wide. They're naturally extensible. Like your integers can typically hold 2 to the power of 32 different values, which is quite wide. Like there's a lot of information you can pack in there if you assign semantics to specific values of the integers. Don't use bools ever in interfaces. They're evil. Usually things start out being binary, and then it turns out there was a third case, but now you've limited your 2 to the power of 32 set of valid values to 2. And you're still even using the same storage. Like, just don't ever use bools. They don't communicate well, they don't behave well, don't use bools. But since you're adding semantic to integers, and integers are also always the same, you usually want some help, and that's where the enumerators come in. But you don't want enumerators in signatures, because first of all, they're difficult to translate, and they're integral but not necessarily int. And of course, we want binary stability and binary you want to be able to predict exactly what the layout that function exists from your FFI. And integers, they know how to deal with, but they don't know about your enumerators. So use them for that for communication and documentation purposes, but don't use them in signatures. As named constants, they're obviously fine. Enough about ints. Let's talk about allocations. Don't do them. The problem with allocation is that they introduce a lot of complexity. There's a lot of questions that arise that are sometimes subtle and sometimes not, that you will quickly get bitten by if you allocate a lot. And this is obviously from the context of the core library, right? So the question is, when you allocate something, like in our blob example, who owns that object? Do you take care of it from the core library? Do you register it somewhere in your own internal object graph? Are they responsible for clearing it? What if they have a different lifetime semantic than you expected? Right? You can actually know that in advance, and the best decision is, of course, to let the runtime deal with that. When I say runtime, I mean the next library developer, right? Which might be writing Python, it might be writing Haskell. Because runtimes, languages, they have different models. They have different models of ownership, and they have different models of lifetimes. And you want to accommodate for them. As we saw in the example earlier, when do you actually free? Right? Very often you would then have to hook custom destructors into your garbage collector, which is deterministic, first of all, but it's also very clumsy. And it forces your callers to store your pointers. Then there's also the question of copying, right? If you just provide a pointer to your structure, you also maybe sometimes need, well, if it's supposed to be copyable, which is often a good idea, it turns out, you would then need to provide a custom copy operation. What if you want to reinitialize something? What if you want to partially initialize something? What if you want multi-phase initialization, which is perfectly viable and interesting in a lot of languages? And also, if you're writing Python, but you're allocating in C, why are you bothering writing Python in the first place if Python's not going to deal with the memory for you, right? Then you're just having a very slow program. That's basically C. You get all sorts of issues, so don't do that. And one of the big problems people tend to have with C or unmanaged languages is that it's very easy to leak memory. But I've solved that problem because it's very easy to not leak memory if you never allocate. So don't do that. But the question then, sometimes you still need memory. Is all lost? What's the alternative? Well, you provide two functions. The first function would be a function for that specific procedure to query the size. So how much memory do I need to provide for this object construction or reading or something to make sense? Well, there is a function for that, and you just say, okay, so how much memory do I need to allocate? And then your client will then allocate his bytes however he feels like it, right? So he's just creating a buffer, and then you take that buffer as an argument to the next function, which then writes the data. So you sort of disconnect the allocation from the population of data. That's surprisingly easy to work with, and it's very comfortable, and it has a lot of benefits because this style enables paging, right? So now you can say, all right, so we're actually going to have to write about 10 gigabytes of memory, but you don't need to allocate a 10 gigabytes array. No, you can allocate 1 gigabyte at a time and call the same function with different parameters every time to sort of page through your entire source of whatever you're going to do. So it works very well with streams, for instance. You can reuse your buffers if you know that you really only need to process a few bytes at a time, but you need new bytes every time. You can now use the same buffer every time by allocating it once from the outside and just calling the function with the same buffer pointer every time. You can do multiple writes in a single buffer, which is something we use to great success in segyio, where we read large, sometimes even or actually very related types sources of data into the same big array, because these are large numeric arrays, and provide a sort of different lens on this seismic, which is very useful. It supports different allocation strategies. If you want to use your arena, if you want to have an object pool, if you want to have concurrent allocations, this is not possible because you're allowing the library writer to make that call instead of you. And of course, memory is now always registered with the host, which means that it naturally works with their garbage collector. So the question then maybe is, what does this actually look like in practice? What is the consequence in code? So this is lifted almost verbatim from our source code. I've simplified and cleaned up a few names for the sake of fitting on a slide. But this is what it looks like from Python. So in Python, we use NumPy and says, all right, so this is the shape of the memory I'm about to need of the data that your user just asked for. And this is its type. Usually that is a 4-byte float, but not always. And then I'm calling this getTrace function or getTR function, and I'm passing it this buffer as an argument. In the Python extension, which is technically written in C++, I actually just lift that buffer from that was now allocated in Python. As you can see, it's allocated in Python code. I get that internal pointer, and I pass that into the core library. The core library never actually doesn't know that Python is the one driving it. It just says, all right, so I have this memory that I'm being given, and I'm being asked to get this data, and I'm just going to write it in there. Because we can assume that our users are library writers and they know what they're doing, we're not checking boundaries, we're not checking that this memory is actually valid or anything, because we assume that they've already dealt with that. And of course they have a much easier job of doing that because we're offloading that job to NumPy. And this actually gives us a lot of opportunities. It allows us to now allocate a shape to get a matrix. Right? Shape does not now have to be one-dimensional, it can be two-dimensional. We can actually write this into a different object. We typically use NumPy arrays, but you could have used something from a BLAS object, you could have used an X array, or any kind of object really. We're not very picky on that. An optimization we do is that when we're writing or when we're detecting that we're being used in a for loop, which you can in Python by realizing that or recognizing that you're coming from an iterator or the iter call, we actually reuse the buffer. So you use a single buffer even though you're reading the full file. So you're using typically maybe 2 kilobytes of memory to read a 10 terabyte file, which is quite cool. Of course, this calling style is still very un-Pythonic. But as I alluded to before, this is still deep inside the library, and the user never actually sees this interaction. Something that isn't very clear from this slide is how we're actually calling the core functions and what that sort of entails. So one thing, in order to maintain future and backward compatibility, I recommend always doing this. So there is never ever an excuse for not checking the error code. Something can go wrong and you want to report it as nicely as you can to your users. But sometimes we end up getting more descriptive error codes as time goes on because we discover more edge cases, right? So what you should do, if you're actually wanted to care about it a lot, you should switch over your error. It's an int, so of course switching is cheap, and the branch predictor is going to help you a lot. And then you have your OK, which is usually OK, fine, go on. And if not, then you handle the errors that you know about, but always have the default case, which is to just propagate the error back up. Usually in Python, we will end up throwing unknown error, which is fine, but the point is that is still now handled, and we never get into the risk of having silently corrupted data but continued execution. The shorthand of that is to just check, is this non-zero, because OK was, or the success code was very carefully chosen to be 0 in order both to enable the style and also because on at least Intel, checking for 0 is faster than checking for non-zero, which is very convenient, right? So then if there is an error, just return it back out. We've actually used this before because we have added error codes to functions. And then we just used this to discover whenever we were missing a case. But at least that code was now not completely broken. Maybe a little bit less use for error message for a while, but over time these tend to converge against better error messages because the runtime, the library now has more opportunities to be precise. But this is without changing any code in the runtime. You can now handle cases added. So this is a form of future-proofing. You could argue that the return value is a part of the binary interface for a certain class of errors. That would be a very interesting discussion. From this perspective, it kind of defines saying you're not allowed to assume that the function will always return the same error across multiple versions, in particular because sometimes we add error codes for not supported yet, basically. This is the slightly abbreviated list of the error codes that we can return, and we try and describe what exactly went wrong for multiple or for our functions. And these are of course reused because you always have the context in which this was returned because you know the name of the function that returned it. So invalid field means actually different things, a little bit depending on where you're calling it from, but that's fine. Of course, the return types are always ints, but we're choosing our integers from this table. So let's talk about primitive functions. Because now we know how to call them. So let's look at how to combine them combine the no allocation primitive type signature function lessons into, the full picture. Getting up to version 1, it takes a while, because what you want to do is to try and identify the set of atoms that would solve your underlying problems. You want your core library to always be a part of the decision what something means. It means a lot of functions that just look up to a table or return a set of predefined strings, and that's fine. But you want that authority to be within your core. Of course, your runtimes are free to choose to ignore that when it's convenient, but overall you want at least that to be available. You want your runtime libraries, your Python library, for instance, to really only massage arguments and provide an interface to the Python users and have all the actual action happening in the core. And really, this is just good software design, right? Your functions should have a single responsibility and should be very clear in their contract. One thing I have noticed is about segyio itself, actually, is that even with our quite low-level interface, I really wish it was even lower level sometimes, right? I would have had even more details to play with. Because when they don't work, they can be augmented. But now I need to add more, clumsy and different functions. Because remember that our users would be other library developers, and they want to be able to turn knobs and to make these decisions for themselves because they have the context that they want to apply this in, right? But ideally, if two functions can be combined to produce a result, don't add the third function that is just a combination of the two, because your users might want to be able to inject something in the middle. And they're adults, they know how to call multiple functions anyway. That's not your issue. In order to design them, I have a few guidelines. And I'm actually very happy with this term outside in wiring that's here. Because it makes it very clear what state and what data is actually needed to compute, right? Something. So for instance, we have a function that is called trace size or something. And that takes, I think, 6 parameters. And by looking at that signature alone, you know exactly what data do I need to provide in order to compute the size of a trace. Trace is a concept from Seismic. It's a single line of data from the boat, usually, reflected back from different types of rock. So it makes it very clear what data is needed. And it allows the consumer, your library, to initialize and prepare properly. Maybe they want to sometimes cache, maybe they want to load something from disk, maybe they want to multi-phase initialize. But that choice is now up to them, not up to you. If you heavily parameterize your functions, your features can be, your feature selection can be done by storing values instead of storing dispatch tables, which is very convenient. That means you can actually add a set of new algorithms and procedures, and you can switch between them with an integer without, rather than having to select different foreign functions to call. It allows overriding at every step. And there's a case study in that. So for instance, let's assume you want to enumerate a lot of data on disk, but you know that they're almost the same size always. You can, of course, compute that index with the function that you, of course, heavily parameterized, and then pass this index as a parameter to every function that actually cares about this, right? What you would often do is that you would store this inside a opaque handle or something in C. But if you instead pass it as a parameter and actually pass it as an explicit parameter that is basically just a pointer to a lot of integers in a row, which are your file offsets, then you can manipulate this from Python and say only care about the first half of the list. Or maybe remove some elements that you know are bad. And that is something that you might want to actually exploit as a Python library writer, or whatever your runtime would be. In our case, it's Python, which is why I keep mentioning it. This wiring, this sort of mixing features together, is now done from the outside, because it's at that point you have the context of what you want to do, right? it's easy to report the error on exactly that step that failed because you know exactly which function that failed and you know that it only did that one thing. And because, of course, your functions are very small and very explicit on the parameters, it can now also be emulated and tested very easily. So a lot of the time we actually emulate errors by just passing different parameters, making the function behave differently, and we observe that that difference is actually happening. So it goes really well for testing as well. Having a lot of functions to do all these things is pretty convenient because it's the assembly of them, it's putting them in order that would solve your problem, but it gives you a lot of flexibility to report and in Python, for instance, raise the right exception at the right time because of that. There is always a temptation of actually solving the problem in Python or in the language you're targeting first. That's usually a mistake, and we made that once. That was very painful to unravel. So I have a quick example on that. This is one of the workhorse functions in Segway.io. It reads one of these traces, a long list of numbers from disk. If you squint a little bit, you will see that this is reading a possibly strided column from a matrix, because in fact our seismic data format is really just a big matrix. So I want to highlight two things. I want to highlight these three. These are your strides, and they're modeled after the steps that you would do when you slice lists in Python. So this is a strided read. Reading a full column is really just a special case of this, where of course your start is your first element, your stop is your last element, and your step is 1. So there's actually not a need to have a function dedicated to reading a full column, because it's just a special case of the stride. The caller, the other library writer, will now be able to dispatch both strided and full column reads with the same function, and it could use runtime parameters to decide which one. There's no need to dispatch between this one, which could read strided, and one that would read a full trace or the full column. And then there's these two. They're a little bit cryptically named. A lot of that comes from the context of the problem that we're trying to solve. So these describe where the data in the file starts and how big, or rather how long in bytes, each of these columns are. Usually you would hide this inside the file handle fp, right? But it has proven very useful to keep passing this about, because that means that we can actually deal with files that aren't completely up to the standard, because, for instance, they were truncated a little bit when they were copied. So we can now actually recover dealing with broken files by manipulating where exactly the data starts. And to be fair, these values are usually provided by the library itself. We provide functions to get the default and the sane and actually the inferred value of these two parameters, but you are able to manipulate them, and that is something we have used to great success. Usually Python never even inspects them, it just passes them along. It also powers actually one of the functions where we're trying to read a sort of parallel ghost image of the file, which is pretty cool. Callers, the other library to Python, can now actually reinterpret traces since we passed the trace size, the size of the column, in bytes, and allowed us to, without any modification to the binary interface, support 2, 3, and 8 byte numerical values. Almost no code change in Python. I think the entire diff is 20 lines, and it's just not failing code that was added. No actual numerics were changed. This function here is probably the one I'm that have. Yes.
So buff, that's something that you pre-allocate in Python, right? But is that a separate function, or will this, if I say have buff be 0, would that give the size or something?
Right. So the question is, if the buff pointer there is allocated in Python, and what happens if it's null? Well, if it's null, then the function crashes, or I think it just returns invalid arguments. But it is, yes, it's something that's allocated in Python. And in order to figure out how large that should be, you have to call a different function that is provided. And that is really just inspecting the size, the number of samples or the number of elements in your columns, and then the size of each element. It's just a simple multiplication. You can do it by hand, but we provide a function for you in order to not having to deal with that distinction. But we never actually inspect the buffer because we know that our users, in this case, would be library writers, and in this case, it's me. So I know that the buffers I'm passing are sane. And in fact, you can assume that because you're not targeting a developer far away trying to build an application for something. You're targeting someone that will care about these details. So that's fine. But of course, because this is not something you would do in all libraries, you would try and help them with allocations, but you shouldn't here for this specific problem. This is a function I'm probably the most happy with. So in segyio, numerics can have a lot of different formats. It can be IBM float. It can be IEEE float in both 4 and 8 bytes. It can be 1, 2, 3, 4, and 8 bytes signed and unsigned integers in both little and big endian. They're all powered by this interface. This function takes a format which is an integer with a gentleman's agreement. It takes the size in elements, and it's a buffer that it will then change. This is not actually something that could have been done inside the read subtrace function, but in fact it's not. It is sort of separated because that allows us to, for instance, read in a batch, even asynchronously, say 100 columns, like 100 of these traces, and then in a single batch convert them to the CPU native representation. So that splitting of responsibility has proved very, very useful. And actually it allows us to have sources of data that aren't on disk. The alternative to that would very often have been this, which in terms of binary stability would of course be able to provide the same because we just keep on adding functions. But that means that in order to figure out which one to do, the Python library would have to know what format it is, what format the CPU is, and have all these function pointers to dispatch to. Now that is done inside the library, and all that I need to do in Python is to store an integer, which the library has conveniently provided for me. You're encoding the same information, but instead of doing it in a variable, you're doing it in function names, which are a lot more difficult to work with across language boundaries. We've learned to separate I/O from all other logic, and this is one of those ancient programming advices that's still kind of easy to mess up. In particular, because segyio I/O is an I/O library, and how well can you actually separate that? And it turns out you should even do more than what we did. What is the gain of not providing I/O, for instance? Well, right now, our I/O, all our functionality is tied up to our special segyio handle, right? The problem with that is now that we maybe want to work on memory mapped files or even files in the cloud, that turned out to actually be a showstopper for a lot of functionality. And the thing is, what really is I/O? Well, I would argue that this toNative function is a type of I/O because we're now doing a memory transaction across the language boundary, which is very similar to doing a memory transaction across a physical boundary between the CPU, or sorry, between the disk and the memory. When we, maybe half a year ago, we added support for another 6 or 7 numerical formats without any change. Just Python silently accepted more files where it used to crash and now didn't anymore. That was all the difference that our users would notice. And this enables, I think, good integration. It allows us to translate partial buffers, which is nice if you just want to, say, for instance, translate half of your buffer, or maybe you want to read in batches and translate in batches. And as I mentioned before, your source data does not actually have to be segyio. It could be read from a pipe or something, and you would still be able to use this function. because it's not tied to the I/O itself. And with that, I say thank you. And if there are any questions, then I'm happy to take them. We already had one. Any questions? All right. Thank you very much.